On Wednesday, we talked about 9.3, which has to do with the normal distribution and z-scores. And so before I get into the actual problems, I want us to remember that the normal curve, so in a normal curve, the mean, or mu, is 0, and the standard deviation, or theta, is 1. So if we think about our normal curve, it is this nice bell curve with our mean here in the middle, which is 0, and then we have our standard deviations. Which is 1. So when we look at this, we've got one standard deviation in each side. When we look at the standard deviations to the left of the mean, they're negative because they're less than the mean. And then we have the standard deviations on the right side, they're positive because they are greater than the mean. And then we have these what am I trying to say? These things that we found. So we have z-scores. So the z-score is equal to the standard deviation on a normal curve. So if z equals 1, that's one standard deviation. But then we end up with these other amounts in here where you could have a z-score equal to like 1.5 or 0.75 or even say negative 1.25. These are all possible z-scores. And so what those are measuring are the number of standard deviations from the mean. And so a z-score of 0.75 is 0.75 of a standard deviation from the mean, or a z-score of 1.5 is 1.5 standard deviations from the mean. Negative 1.25, excuse me, would be 1.25 standard deviations to the left of the mean. Okay, so when we think about z-scores, there's two ways that we can find them. So z-score is, we've got z equals x minus the mean over theta, or you can also see it as x minus the mean as mu over theta. So remember, x bar is your mean and theta is your standard deviation. So we would use this when x is known. We also have a calculator function called inverse norm, and we want to use that when they're telling us the area under the curve, so like 12%, 20%. So inverse norm, we'll find our z-score. When a percentage is known. And that function is going to be inverse norm. And then you've got your percentage value, and then we have, what is it, 0 and 1. And this percentage is percent to the left of the mean. And we saw this in our notes on Wednesday when we were looking at finding, I'm trying to see which one it was on. It was when we were looking at the calculator option when we were trying to find the z-score for 12.1% of the area to the left of z, we used this. And we're going to use this again in some of the examples that we're going to do today. Another formula that we used was normal CDF. When we put that in our calculator, there's pieces that we put in. So the normal CDF has to do with finding the area under the normal curve. And with this, we have to find z-scores in order to be able to use this application. So we think of this as being our lower bound. This is going to be our upper bound. And then this is always going to be 0 because that's the mean on the normal curve. And the second part is going to be 1 because that's the standard deviation on the normal curve. So all of this information here is what we're going to end up using to solve these problems. Okay. So any questions about this before I move forward? Okay. 1 second. I'm just going to mark. Okay. So we go to our first problem. It says find the percent of the area under a normal curve between the mean and the given number of standard deviations from the mean. Again, they're telling us normal curve. So with a normal curve, the mean or X bar is equal to 0. And the standard deviation is 1. So you can see in our first example, we have 1.7, which means it's 1.7 of standard deviations from the mean. So if we draw a picture to represent this, we've got our curve. It's a terrible curve. Okay, and in the middle here, we have our mean, which is 0. And then we're going to do 1.7 as a z-score. And we're saying the area under the curve is this amount right here. So in order to calculate that, we're going to do normal CDF. Our lower bound is going to be the mean. Our upper bound is going to be 1.7. And then again, because we're dealing with a normal curve, the third number we put in is the mean, which is 0. The last number is 1 because that's our standard deviation. So again, this is the lower bound. This is the upper bound. This is our mean. And this is our standard deviation. So your homework wants you to report this as a percent. And so first, let me stop sharing for a hot minute so I can get my my calculator up, okay? Okay, so we're going to turn this on. Again, to find this normal CDF, we hit second, and then the vars key, which the second part gives us distribution, the DIS TR, and we're going to want normal CDF. So we go down 1. When we think of CDF, remember our previous experience with it was the binomial CDF, and that was finding the range, the probability within a range of values. So it makes sense that we're using this normal CDF to find the area range for a normal distribution. So again, we've got a lower bound, an upper bound, our mean, and our standard deviation. So we're going to put enter. We're going to do 0, 1.7, 0, 1, And we're going to press enter and we get 0.4554. I'm taking it out 5 decimal places because your homework wants you to convert it to a percent and round to 2 decimal places after converting, which gives us 45.543, which once we round, we get 45.54% as our answer. So 45.54% of the distribution exists between the mean and 1.7 standard deviations from the mean. Again, we're just looking at that upper bound. If we were to make this symmetrical, we would have negative 1.7 up to 0, which would give us the same percent. Together, then we would get 90% of the data between those 2 points. But again, we're just saying from 0 up to 1.7, we're just looking at that range right there. Number 2, we've got negative 1.45. So now we're looking on the left-hand side. So if we draw our curve, we still have the mean in the middle, which is 0. But now we're looking to the left, which is going to be negative 1.45. Negative 1.45 is not as far away from the mean as 1.7 is. So we would expect our value to be a little smaller than what we found in part 1. And so for this one, because when we're putting this in, we've got the normal CDF, and we always list the lower bound first. And so for our lower bound, we've got negative 1.45. Our upper bound is 0. We then still have 0 and 1. It's always going to be 0 and 1 in those second 2 positions. And I want you to go ahead and you do this calculation yourself and send me your answer as a percentage rounded to 2 decimal places. So we're going to do normal CDF of negative 1.45, comma 0, comma 0, comma 1, and parenthesis, and press enter. And we get 0.42647, which is 42.647 or 42.65%. Number 3 says between z-scores of negative 1.83 and negative 0.9. So again, if we do a drawing of this, we've got our mean in the middle. We have a lower bound of negative 1.83 and an upper bound of negative 0.91. And we're looking at the space in between here. So I want you to calculate this one on your own. Think about what we're putting in. So you're going to do normal CDF, but you need to fill in those first 2 positions. And again, send me your answer as a percentage rounded to 2 decimal places. So our lower bound is at negative 1.83. Our upper bound is negative 0.91. So when we put this in, we're going to do, again, normal CDF, negative 1.83, comma, negative 0.91, comma, 0, comma, 1, and we get 0.147786, which becomes 14.7786, or approximately equal to 14.78%. So this process, we already were given the z-scores, and so this process is what we're going to apply to the next problem, but we need to actually find the z-scores in the next problem. So here's what I'm talking about. It says a certain type of light bulb has an average life of 500 hours with a standard deviation of 100 hours. The length of the life of the bulb can be closely approximated by the normal curve. An amusement park buys and installs 10,000 such bulbs. Find the number that can be expected to last for each time period. So if we draw the curve here, and we use the information that they have, so we have a mean of 500 hours, and then we've got standard deviations of 100 hours, which would be 600, 700, 800. I'm just doing 3 standard deviations out. The other way we'd have 400, 300, and 200, okay? Just because we have what those amounts are in terms of the actual hours, doesn't mean we can use them with our formulas. We have to think about superimposing this onto the normal curve, which means our real mean is 0, and we have standard deviations of 1 and 2 and 3, or -1, -2, and -3. So when we think about number 1, it says less than 500 hours. So if I were to draw this, $500 hours is the mean, which is 0 right here. And we want less than 500 hours. So remember, for less than 500 hours, we have half of it covered, right? So we would know that it's going to be half of those possible. But let's go through the process to show why this comes out. So the first thing we would need to do is find the z-score. Well, we know that the z-score is 0, okay? So if we do normal CDF, we need to have a minimum amount down here. And down here is where we use -e, or -1 times e to the 99, because we want everything to the left of it. We do 0, 0, 1. So we should get 0.5 here. So if we put this into our calculator, we're going to do second bars Go down to normal CDF. So we want to do -1, and then to get the E part, we do second, and then the comma, which gives us that E in 99. Remember, -1 E 99 is close to -infinity as we can get, because this curve does extend infinitely in both directions. And so the lower bound has to be -infinity. So then we're going to do up to our mean, which is 0. Then we're going to do another comma, which is 0. And then another comma, which is 1. So remember, it's the last two are always 0 and 1, because 0 is our mean, 1 is our standard deviation. And when we press enter, we get 0.5. And the reason why it's not exactly 0.5 is because we're using an approximation for infinity, meaning we're using -e to the 99, but is actually just -infinity. So we're going to use a rounded amount of 0.5 here, because that's what it is really if we were able to have -infinity. And again, we know that it's half the curve. So then we're going to take 0.5 and we're going to multiply it by the number of bulbs we have, because it's telling us 50% of the distribution, that's what the area of the curve represents. It's the amount of the distribution. 50% of that is going to last less than 500 hours, which gives us 5,000 bulbs. Again, we can look at that and say, all right, well, obviously, it should be 50%. It should only be half. But why? What is the steps that we would take to do that? Okay. So for number 2, it says between 350 and 500 hours. So if we were to look at our table up top, not our table, excuse me, our graph, it's going to be this space over here on the left, sort of right in here, right? But we don't know what those Z-scores are that are associated with that. And because it's going to go slightly past the mean as well, because it goes to 550. So we need to find the Z-scores for 350 and 550. Now remember, to find the Z-score, we have X minus X bar over the standard deviation. So that means we're using X equals 350 and X equals 550, a mean of 500, and a standard deviation of 100. So I want you to find the Z-score for 350 and find the Z-score for 550 and send those to me in a direct message. So the Z-score for 350, we're going to do 350 minus 500 over 100, which gives us, what do we get here, negative 1.5. And the z-score for 550 is going to be 550 minus 500 over 100, which is going to be 0.5. So in order to find the area under the curve that exists between those two spots, we're going to do normal CDF, and we're going to go with the bounds. So remember, your first value is always a negative 1.5. And we're going to do negative 1.5, comma 0.5, comma 0, comma 1. And I want you to go ahead and find this value to, what do I want? 5 decimal places. So if we put this in, we end up with 0.624655. So we're going to take this amount because that is the portion of the distribution that is between these two amounts. So if we think about this in terms of what percentage, 62.4655% of the light bulbs are going to fall in that range. So we want 62.4655% of 10,000. So we're now going to take 10,000 and we're going to multiply it by this. And we end up with 6,246.55 bulbs. And your homework's going to have you round to the nearest bulb. So we're going to say 6,247 bulbs. Okay, so number 3 says more than 440 hours. So if we bring number 3 down here, we think about our curve. We've got our standard deviation here in the middle. And so 440, remember our mean, is 500. So 440 is going to be like right here. And we want more than that. So we're looking at everything to the right. So the first thing you're going to do is find the z-score. And so if we're going from here, that means we're going to have 1E99 on the right-hand side as our upper bound. So then we're going to do normal CDF. And then we're going to take that amount and we're going to multiply it by 10,000. So I want you to send me your final answer, round to the nearest whole number of what you get. Okay, so again, your steps are going to be first find the z-score, then do normal CDF to get the percent of the area, or to get the percent of the data or the area under the curve that represents that space, and then you'll multiply it by 10,000 to get your final answer. So finding the z-score means we're going to do 440 minus 500 over 100, which gives us a z-score of negative 0.6. So from here, we're going to do normal CDF of negative 0.6, comma 1E99, comma 0, comma 1, which gives us 0.725747 rounded. And then we're going to take that and times it by 10,000. Which gives us 7,257.47 or 7,257 bulbs. So I want to skip to my last example because I think that's a harder example. And then if I have time, I'll come back to the one I have next in the notes. So my next example was this oatmeal one. I'm going to skip to a teacher giving a test to a group of students. So teacher gives a test to a large group of students. The results are closely approximated by the normal curve. The mean is 76 with a standard deviation of 8. The teacher wishes to give A's to the top 8% of the students and F's to the bottom 8%. A grade of B is given to the next 20%, with D's similarly. All other students get C's, and find the bottom cutoff rounded to the nearest whole number for the following grades. So let's look at our curve first. Actually, let's do this down below. There's more room down here. So if we think about our curve, we've got our mean in the middle, which is a 76, okay? Now we have those standard deviations, but ignoring those, we've got these points on either side. So in here, this is where the C's live, okay? The cutoff for a B, we have 20% of the data. In A, we're gonna have 8%, is that what it says? Yes, 8%. On the other side, we have D's, which is 20% of the data from D down to F, and then F is going to be for the last 8%. Okay. So if we think about what are the C's, well, if we take 100% minus the sum of the two sides, 8 and 8 is 16, 20 and 20 is 40. So we're going to minus 56%. Which gives us 44%. So 44% of the data is going to live in here. So we think about our A's, the percent of the data that's to the left of the A is all this stuff. Okay. So the area to the left of A is 92%. And how do I get that 92%? Well, 8% represents the A's. That's to the right, A and above, 8%. The rest of it has to be 92% or 100 minus 8%, which gives us 92%. Now, in the beginning, I was talking to you about the inverse norm function, and we use it to find the z-score when we don't know X. And so what I'm saying is that we don't know what the A cutoff value is, which is what we would normally call X. We know what our mean is. We know the standard deviation, but again, we don't know what that X is. So in order to find the z-score, because we have the percent of the data, we're going to do inverse norm. So again, to find Z, we're going to do inverse norm of, oh geez, 0.92, comma 0, comma 1. So the 0 is the mean on our normal curve. The 1 is the standard deviation on the normal curve. Again, we're imposing this distribution on a normal curve. So we're saying 92%, that's the area under the curve, is represented there. That's what's to the left of it. And so we're going to put this into our calculator. And to get the inverse norm, we hit second distribution, and we go down to number 3, which is inverse norm. And that's the inverse of the normal curve is what it stands for. So from here, we're going to put 0.92, comma 0, comma 1, and parenthesis. And we get 1.405, blah, blah, blah. We're going to just round this to 1.41. So when we think about where this cutoff for A is going to be, it's going to be, this represents 1.41 standard deviations from the mean is where the cutoff is. So if we go back to our problem and we think, okay, well, our mean is 76 and our standard deviation is 8. So I want to add 1.41 of those standard deviations onto the mean. So we're going to take 1.41 and times it by our standard deviation, giving us a cutoff of 87.28, and you're going to round to the nearest whole number here. So we're going to have a cutoff of 87 for A. So let's think about the lower cutoff for C, the initial cutoff for C, because that's what this this represents. So this grade of C means the lowest grade possible for a C. That's what they're trying to say here, okay? So area to the left of our C, again, this whole purple region is what is C. So the area to the left of C is right here. So we have 28%. We don't have to subtract this off of 100 like we did for the A's because we were looking at the other side. We're just saying, okay, it's already to the left. We can use it as it is. So I want you to find the Z score and then tell me what the lowest grade is that we would need for a C. So think about what we did in A and try that for finding the C. So we're going to do inverse norm of 0.28, right? 28% becomes 0.28, comma 0, comma 1, which gives us we're going to do 0.28, comma 0, comma 1, end our parenthesis. And we get negative 0.58 to 8, blah, blah, blah. Again, we're only using a z-score rounded to 2 decimal places. So we're going to do negative 0.58. Again, this is negative 0.58 standard deviations from the mean, which means it's to the left of the mean. And so we're going to take 76 plus negative 0.58 times our standard deviation. So 76 plus negative 0.58 times 8, giving us 71.36, which we round to 71 as our lowest cutoff score for AC. Okay. So questions about that? So we only have 1 minute left. I just want to talk to you really quick about the box of oatmeal problem, just so you know how to go about starting this. So a box of oatmeal must contain 16 ounces. The machine that fills the oatmeal boxes is set so that on average a box contains 16.5 ounces. So the on average means that our mean is 16.5 ounces. I don't know why I wrote a percentage sign, it's ounces. And the boxes filled by the machine have weights that can be closely approximated by their normal curve. So again, that whole closely approximate by the normal curve means we're imposing this data on the normal curve, which means we're going to need z-scores. And so it says what fraction of the boxes filled by the machine are underweight. Sorry, this is supposed to be if the standard deviation is as follows. So for number 1, we have a standard deviation of 0.5 ounces. So what we need to do is we need to find the z-score. So first, find z-score, which for this is going to be our amount is 16. That's the lowest cutoff, minus the mean of 16.5 over a standard deviation of 0.5. Okay. So when we do this, we get a -1 for our z-score. So then second is we're going to do normal CDF, because now we're finding the percent, or it's not the percent, but the area under the curve. So we're going to do normal CDF of -E99, because again, we're looking at everything less than that amount. So it's going to go all the way to infinity. So -E99, comma -1, because that's our z-score, and then comma 0, comma 1, and we get 0.158655 or 0.1587, and they're going to have you take it out to 4 decimal places. So for number 2, you would just redo this to find a new z-score, but use 0.2 ounces instead of 0.5 for your standard deviation. So I hope this cleared up kind of what we did on Wednesday, and I hope it helps you with doing your homework. As usual, please email me if you have any questions, okay? And I will see you all on Monday, where I will start going over material for the final, okay? All right, thanks. Have a good day, you guys.